Walk through a rainforest, a coral reef, a savanna. Every animal you see represents a winning streak. But here's what the fossil record shows. Nearly every species that has ever lived is gone. Not some, not most. 99.9%. That statistic comes from comparing the roughly 10 million species alive today against an estimated 5 billion that have existed across 4 billion years of life on Earth. The exact numbers are debatable, but the ratio holds. Extinction isn't the exception, it's the rule. This raises a question most of us never ask. How long does a species actually last? The answer is shorter than you'd think. Mammal species average 1 to 2 million years before they vanish. Marine invertebrates like clams and snails last longer, 5 to 10 million years, but even they rarely break 15 million. Almost nothing does. Homo sapiens has been around for roughly 300,000 years. We're young, and the mechanisms that have erased 99.9% of everything else are still running. We perceive the natural world as stable because our lives are short. A human lifetime spans decades. A species' lifespan spans millions of years. This mismatch creates an illusion. We see a finished world when we're actually watching a temporary frame in a 4 billion year elimination process. The concept of species lifespan works like this. A species originates through speciation, when a population becomes reproductively isolated and diverges enough to be distinct. It terminates at extinction, when the last individual dies. The time between is the lifespan. For mammals, that duration averages 1 to 2 million years. Our own species sits at roughly 300,000 years, making us relatively young by mammalian standards. Marine invertebrates fare better. Bivalves and gastropods, clams and snails, average 5 to 10 million years. The difference traces to environmental stability. Terrestrial habitats, especially during ice ages, shift rapidly. Climates swing between glacial and interglacial periods every 100,000 years or so. Forests become grasslands. Coastlines move. Terrestrial species face constant pressure to adapt or die. The ocean, particularly the deep sea and broad continental shelves, changes more slowly. Temperature swings are dampened. Predators and competitors remain more stable. Species there face less evolutionary pressure to change, so they persist longer. But even marine species hit a ceiling. The 15 million year barrier is rarely crossed. This isn't a hard rule, it's a statistical pattern. The longer a species exists, the more dice it rolls against extinction. Environmental shifts, new competitors, emerging diseases, genetic drift. Eventually, something kills it. Life operates in constant turnover. The species we see today aren't evolution's goal. They're the temporary survivors at the edge of an ongoing experiment. Extinction doesn't only happen during catastrophes. There's a baseline rate, called background extinction, that runs continuously. Paleontologists estimate this rate at about 0.1 to 1 species per million species years. It's the normal churn against which mass extinctions are measured. Several mechanisms drive this background loss. One is the Red Queen hypothesis, named after the character in Through the Looking Glass, who says it takes all the running you can do just to stay in place. Species don't adapt to static environments. They adapt to other species that are also adapting. A parasite evolves a new attack. The host must evolve a new defense or go extinct. Predators get faster. Prey must get faster too, or develop better camouflage, or change their behavior. This creates a relentless co-evolutionary treadmill. Standing still equals death. Local environmental changes also drive extinctions without global drama. A climate becomes slightly drier over thousands of years. Forests retreat. Grasslands expand. Species specialized for forest habitats, a particular tree-dwelling primate, a forest floor insect, lose their habitat. They must migrate, adapt, or vanish regionally. Sea level changes amplify this effect. During ice ages, water is locked in glaciers, and sea levels drop. Vast continental shelves are exposed. The shallow marine ecosystems that existed there disappear. When the ice melts and sea levels rise again, they flood coastal areas, drowning terrestrial ecosystems. This cycle has repeated dozens of times over the past 2 million years. Competition between previously isolated ecosystems also drives extinction. When two land masses connect after millions of years apart, species suddenly encounter competitors they've never faced. The results are often one-sided. The Great American Biotic Interchange is the clearest example. Around 3 million years ago, the Isthmus of Panama formed, connecting North and South America. South American fauna had evolved in isolation. It included giant ground sloths like Megatherium, terror birds, large flightless predators called phorusrhacids, and glyptodonts, which resembled car-sized armadillos. Marsupial predators held the apex positions. North American fauna had been connected to Eurasia via the Bering Land Bridge. Its species had faced broader competition across a larger interconnected landmass. They included saber-toothed cats like Smilodon, Gomphotheres, relatives of modern elephants, horses, and placental carnivores like dogs and bears. When the isthmus formed, species from both continents crossed. The exchange was uneven. North American species dominated in the south. Terror birds, which had been apex predators for millions of years, were outcompeted by the more advanced placental carnivores. Most South American marsupial predators vanished. The North American fauna had been hardened by tougher competition, and when they encountered isolated southern species, the southerners lost. This wasn't about individual superiority. It was about which population had faced more relentless evolutionary pressure before the meeting. The South American species hadn't been tested against the same level of competition. When that test came, they failed. Specialization is a short-term advantage and a long-term liability. When a species becomes highly adapted to a specific resource or environment, it thrives, until that resource disappears. The modern giant panda offers a clear case. It relies almost entirely on bamboo. Bamboo is low in nutrients, so pandas must eat massive quantities daily. This diet works fine as long as bamboo forests remain. But if a blight, climate shift, or habitat destruction removes the bamboo, the panda has no fallback. It cannot switch to another food source quickly enough. Smilodon, the saber-toothed cat, is the fossil example. Its iconic elongated canines were specialized tools. They weren't for slashing. They were for a precise killing bite on large, thick-skinned, slow-moving prey, giant ground sloths, mammoths, mastodons. The sabers would pierce deep into the throat or underbelly, severing major blood vessels. This strategy worked brilliantly for over 2 million years. Smilodon spread across the Americas and became one of the dominant predators. But at the end of the last ice age, around 11,000 years ago, the megafauna started disappearing. Climate change and possibly human hunting pressure decimated populations of the large prey Smilodon depended on. The saber-tooth couldn't adapt. Its specialized anatomy, the elongated teeth, the robust forelimbs for pinning prey, the jaw mechanics optimized for that specific killing bite, became a liability. Smaller, faster prey like deer required different hunting tactics. Smilodon couldn't catch them effectively. Its tools were useless against the new prey base. It starved. This is the specialist's trap. Every adaptation that increases fitness in one environment creates vulnerability when that environment shifts. Generalists, species that can eat many foods, live in many habitats, tolerate many conditions, are less efficient in stable times. But when conditions change, they survive because they have options. Specialists, having solved their environment too well, paint themselves into a corner. Background extinction is constant, but mass extinctions are spikes, brief periods when the rules break down and planetary scale mechanisms activate. The fossil record shows 5 major events over the past 500 million years, each killing more than 75% of species. The Ordovician-Silurian extinction, around 445 million years ago, killed roughly 85% of marine species. A glaciation event dropped sea levels, draining the vast shallow seas where most life existed. When the glaciers melted rapidly, the sudden warming caused ocean anoxia, loss of oxygen, and many surviving species suffocated. The late Devonian extinction, around 375 million years ago, eliminated about 75% of species. Prolonged ocean anoxia again played a central role, likely driven by volcanic activity and changes in ocean circulation. The Triassic-Jurassic extinction, around 201 million years ago, killed roughly 80% of species. Massive volcanic eruptions from the Central Atlantic Magmatic Province released enormous amounts of carbon dioxide. This triggered warming, ocean acidification, and anoxia. The Cretaceous-Paleogene extinction, around 66 million years ago, is the most famous. An asteroid roughly 10 kilometers wide struck what is now the Yucatan Peninsula. The impact released energy equivalent to billions of atomic bombs. It vaporized rock, triggered global firestorms, and threw debris into the atmosphere, blocking sunlight for months or years. The resulting impact winter collapsed food chains. About 75% of species vanished, including all non-avian dinosaurs. But the worst event in Earth's history was the Permian-Triassic extinction, around 252 million years ago. It killed an estimated 96% of marine species and 70% of terrestrial vertebrates. Life came closer to complete annihilation than at any other point. The cause was the Siberian Traps, one of the largest volcanic events ever. Over roughly 1 million years, eruptions covered an area the size of Western Europe, with lava up to 3 kilometers thick. These eruptions released massive amounts of carbon dioxide and methane. Global temperatures spiked by 8 to 10 degrees Celsius. The warming set off a cascade. Warmer water holds less oxygen, so the oceans became anoxic. Acidification increased as CO2 dissolved into seawater, killing organisms with calcium carbonate shells. In the oxygen-depleted oceans, anaerobic bacteria thrived. These bacteria produce hydrogen sulfide, a toxic gas. Hydrogen sulfide built up in the water and eventually bubbled into the atmosphere, poisoning terrestrial life. The kill chain is visible in the rock record. Carbon isotope ratios show a massive negative spike, evidence of a die-off releasing huge amounts of organic carbon back into the environment. Oxygen isotope ratios show the temperature increase. Sulfur deposits indicate the volcanic source. Each line of evidence narrows the timeline and confirms the mechanism. Recovery took roughly 10 million years. For 10 million years after the Permian extinction, biodiversity remained depressed. Ecosystems were simplified. Only the hardiest, most generalized survivors persisted. Slowly, over millions of years, new species radiated and filled the empty niches. This is the pattern of mass extinctions. A catastrophic trigger activates multiple kill mechanisms simultaneously: warming, acidification, anoxia, toxic gas release. Species face threats from every direction at once. The specialists die first, then the generalists. Only the lucky few in isolated, stable refuges survive. A handful of species and lineages have survived for hundreds of millions of years, seemingly defying the turnover. These living fossils are often held up as exceptions, but they actually reinforce the rule. Their survival depends not on superiority, but on luck, isolation, or living in environments that remove them from evolutionary arms races. The coelacanth is a lobe-finned fish thought to have gone extinct with the dinosaurs 66 million years ago. Then, in 1938, a live specimen was caught off the coast of South Africa. The species had survived in deep-sea environments, stable zones with few predators, little competition, and slow environmental change. The deep ocean is evolution's slow lane. Species there face less pressure to adapt, so they can persist largely unchanged. Horseshoe crabs have a body plan that has remained stable for over 450 million years, predating most dinosaurs. They are generalists, living in shallow coastal waters and eating almost anything organic they encounter. Their survival isn't about perfection. It's about occupying a niche that hasn't fundamentally changed in 500 million years. The ginkgo tree dates to the Permian period, over 270 million years ago. It survived the Permian-Triassic extinction and persisted through subsequent upheavals. By the time humans encountered it, wild ginkgos existed only in small, isolated pockets in China. The tree survived because it found refuges where competition was low and conditions remained stable. These species aren't better than those that went extinct. They got lucky. They occupied environments where the normal pressures, competition, predation, climate volatility, were reduced or absent. Evolution didn't stop for them. It just slowed down. And because the fossil record is incomplete, we don't know how many other living fossil lineages existed and then vanished without leaving a trace. The lesson, survival over deep time, is mostly about avoiding the grinder, not winning against it. Small populations face a specific danger called the extinction vortex. It's a feedback loop where population size, genetic diversity, and adaptability spiral downward together until the species disappears. Here's how it works. When a population shrinks, individuals are forced to mate with close relatives. Inbreeding increases. Harmful recessive mutations, normally masked in large populations, get expressed. Birth defects rise. Fertility drops. The population becomes sicklier. Simultaneously, genetic diversity declines. Useful genetic variation is lost to random chance, a process called genetic drift. In large populations, drift is weak because sheer numbers preserve variation. In small populations, drift dominates. Useful genes can vanish by accident, not because they're disadvantageous. As genetic diversity shrinks, the population loses its ability to adapt to new threats. A novel disease appears, a drought hits, a new predator arrives. The population lacks the genetic variation needed to respond. More individuals die. The population shrinks further. Inbreeding accelerates. Genetic diversity drops faster. The vortex spins tighter. Cheetahs are a living example. Genetic analysis shows that all living cheetahs are extremely closely related, effectively as similar as identical twins. This suggests the species went through a severe bottleneck around 10,000 years ago, possibly during the megafaunal extinctions at the end of the last ice age. The population crashed to a tiny number, and all modern cheetahs descend from those few survivors. The consequences are visible today. Cheetahs have high rates of infertility. They're unusually susceptible to diseases because their immune systems lack diversity. A single pathogen that affects one cheetah is likely to affect all of them. The species is functionally on borrowed time. The woolly mammoth offers a clearer view of the vortex in action. Most mammoth populations went extinct around 10,000 years ago, but one group survived on Wrangel Island in the Arctic Ocean until roughly 4,000 years ago. Genetic analysis of their remains shows they were trapped in an extinction vortex. The isolated population accumulated harmful mutations through inbreeding. One mutation affected their sense of smell, critical for finding food and mates. Others likely reduced fertility, immune function, and general health. The Wrangel mammoths didn't go extinct because of climate change or human hunting. They were already doomed by their own genetics. The vortex made recovery impossible. Even if conditions had improved, the population lacked the genetic health to expand. This mechanism probably operates invisibly in many species alive today. A population crashes due to habitat loss or overhunting. It recovers numerically but remains genetically impoverished. Decades or centuries later, it vanishes, and the extinction is attributed to some immediate cause, a disease, a bad winter. But the real killer was the vortex, set in motion years earlier when the population first shrank. Current extinction rates are not normal. Background extinction, the rate during stable periods, sits around 0.1 to 1 species per million species. Current estimates, including those from the UN's IPBES report, place today's rate at tens to hundreds of times higher. Some assessments go as high as 1,000 times the background rate. By every scientific measure, we are in the opening phase of the planet's sixth mass extinction. This extinction is unique because it's caused by a single species, Homo sapiens. The mechanisms are straightforward and well documented. Habitat destruction is the primary driver. Deforestation for agriculture, urban expansion and infrastructure removes the places where species live. When their habitat is gone, they die. Overexploitation is second. Humans hunt and fish species faster than they can reproduce. The passenger pigeon once numbered in the billions. It went extinct in 1914 due to relentless hunting. The dodo, Steller's sea cow, and countless other species followed similar paths. Invasive species are the third mechanism. Humans, intentionally or accidentally, move organisms across the planet. Rats, cats, zebra mussels, brown tree snakes, and countless others reach ecosystems where they have no natural predators. They devastate native species that never evolved defenses against them. This is the Great American Biotic Interchange on a global scale, happening in decades instead of millennia. Coextinction chains are the fourth mechanism. Species don't exist in isolation. They depend on each other. When a specific pollinator goes extinct, the plant it pollinated may follow. When a prey species vanishes, its predators may starve. Extinction is contagious through ecological webs. The more specialized the relationship, the faster the cascade. But the mechanism now accelerating all the others is climate change. By burning fossil fuels, humans are releasing massive amounts of carbon dioxide into the atmosphere. This is causing global warming, ocean acidification, and ocean anoxia, the same mechanisms that drove the Permian-Triassic and Triassic-Jurassic extinctions. The parallel is exact. The Siberian traps released carbon dioxide, global temperatures spiked, oceans acidified, oxygen levels dropped, anaerobic bacteria produced hydrogen sulfide. The biosphere collapsed. Today, humans are releasing carbon at a rate that rivals or exceeds the Siberian traps. Global temperatures are rising, ocean pH is dropping, acidification is measurable. The mechanisms that killed 96% of species 252 million years ago are activating again, this time because of us. The difference is speed. The Permian extinction unfolded over roughly 1 million years. The current changes are happening in centuries. Species that might have adapted over thousands of generations are being hit faster than they can respond. Homo sapiens is roughly 300,000 years old. The average mammal species lasts 1 to 2 million years. We're young. We're also in a strange position. We're the most successful species in Earth's history by some measures. Global population, technological reach, ecological dominance. We have no natural predators. We occupy every continent except Antarctica. We've reshaped ecosystems on a planetary scale. But this success is built on a strategy that's now destabilizing the biosphere we depend on. We survive by manipulating our environment. We clear forests, divert rivers, mine minerals, burn fossil fuels. For most of our history, this strategy worked because the planet was large enough to absorb the impacts. We were a small population with limited technology. We could overexploit one area and move to another. That's no longer true. We've hit planetary boundaries. There's nowhere left to move. The systems we depend on, climate, oceans, soil, freshwater, pollination, are breaking under the pressure. This creates a paradox. The strategy that made us successful, environmental manipulation, is now our vulnerability. We've become specialists in reshaping ecosystems, and like all specialists, we're painting ourselves into a corner. If the systems we've destabilized collapse, we collapse with them. The fossil record shows that no species is exempt from extinction. Dinosaurs dominated terrestrial ecosystems for 165 million years, far longer than mammals have existed. They were unimaginably successful. Then an asteroid hit, and they vanished in less than 1 million years. Success doesn't guarantee survival. Duration doesn't either. The longer a species exists, the more chances it has to encounter a threat it can't handle. Homo sapiens has existed for 300,000 years. We've rolled the dice 300,000 times and won. But the dice are still rolling. The planet will be fine. Life recovered from the Permian extinction. It took 10 million years, but new species radiated, filled niches, and rebuilt complex ecosystems. Life is resilient over deep time. Individual species are not. The question isn't whether life survives. It will. The question is whether we do and what we take with us. The mechanisms that erased 99.9% of all species are still running. They don't make exceptions. We're subject to the same rules as every other organism that ever lived. Extinction is the rule. Survival is temporary. And the clock is always running.